If you look back at the example we did of using Newton's method to approximate the x-intercept of a function, the algebra that we did at each stage to find the x-intercept of the tangent line was actually the same. And it felt very repetitive to have to do the same algebra over and over again. Well, whenever that happens in math, whenever you find yourself doing the same process over and over again, what you should do is do all that algebra, but instead of having particular numbers or functions, do that calculation just with variables. And then what you'll end up with is a formula that kind of encapsulates all of that algebra. If you think back to when you first learned to solve quadratic equations, probably you started out by completing the square, and then once you solved many equations by completing the square, you got sort of frustrated with how samey all of those problems were, and then you completed the square on a general equation that looked like ax squared plus bx plus c equals 0. If you complete the square for this equation, what you get is you get the quadratic formula, minus b plus or minus, the whole thing, the quadratic formula, right? So anytime there's some algebraic process that is the same every time, do it with you can do that process with variables or labeled constants instead of particular numbers, and what you'll end up with is a formula that encapsulates that algebraic process. Well, we can do the same thing with Newton's method. Instead of starting with a particular number for our first approximation, let's just start with some named constant, x sub 0, and instead of a particular function, let's just start with the function f. Now, of course, we won't have a formula for f, so when we talk about the derivative of f, we'll just have to write f prime, but that's okay. So remember that this should be an f right here. So remember, the first step to Newton's method is, once we have an initial approximation for our x-intercept, is go to the point on the graph. Well, the corresponding point on the graph is x sub 0 comma f of x sub 0. So there's no more algebra or computation we can do for this point, since we don't have a formula for f. Okay. The next thing we need to do is find the equation of the tangent line at this spot. So for the equation of the tangent line at x naught, well, we need the slope of this tangent line, but that's going to be the derivative of the function at this x value. So there's our slope. And we have a point on the line, that's x sub 0 comma f of x sub 0. So now we can write the equation of the line. The equation is y minus the y-coordinate of the point, which is f of x sub 0, equals the slope, which is f prime at x sub 0, times x minus the x-coordinate of the point, which is x sub 0. Okay, now remember, we were going to find the x-intercept of this tangent line. And to find the x-intercept, you plug in 0 for y. So we get minus f of x sub 0 equals f prime of x sub 0 times x minus x sub 0. And then we just solve this for x. So let's divide both sides by f prime of x naught. So minus f of x sub 0 over f prime of x sub 0 equals x minus x sub 0. And then move this x sub 0 to the other side. I'm going to do this over here. So we get x equals x sub 0 minus f of x sub 0 over f prime of x sub 0. Now, when we first developed Newton's method, remember, we called it, if our first guess was x sub 0, our next guess, we called that x sub 1. So this is actually the formula for x sub 1. Well, now we would just repeat Newton's method, but this formula is Newton's method, right? If we want to find what x sub 2 should be, we should just use this exact same formula, except instead of x sub 0, we should be using x sub 1. So x sub 2 would be x sub 1 minus f of x sub 1 over f prime of x sub 1. But then to find the next so x sub 2 would be, right, up to the graph, down to the x-intercept. There's x sub 2. And then for x sub 3, we would just do the same thing, except instead of using x sub 1 in this formula, we'd use x sub 2. So x sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. Well, you can see to generate our sequence of approximate solutions, we're just going to keep doing this. Use this same formula, except at each stage you take the result of the previous stage and use that as the x value for your next stage. The general way to write that is if we, at some point we'll have some x value, at stage n we'll have just produced some approximation, call it x sub n, and then the formula for the next approximation, so x sub n plus 1, this subscript is just telling us what step we're on. So what we're saying is, to get the next step, you take the previous step and then subtract f of the previous step over f prime of the previous step. All right. So this formula, although it came from the geometry of sort of sliding down the tangent line until you get to the x-intercept, this formula is what people usually call Newton's method. So Newton's method looks like this. It's much less geometric, but it's also much more straightforward to compute. So to approximate a solution to an equation like this, where you have some function equal to 0, or to find the x-intercepts of this equation, first guess some approximate solution, x sub 0, and then generate a sequence of approximate solutions using this formula. And you can stop when you reach your desired accuracy, or when you've done as many steps as you feel like doing, depending on the situation. As long as your initial approximation, x sub 0, is close enough to some x-intercept, this sequence of approximations should rapidly get very, very close to the x-intercept that you are looking for.